Hi, Assalamualaikum warahmatullahi wabarakatuh. I am NURAIN MIEZA binti Muhammad SARIP and I will present for question 2.
And I is Muhammad RAHIMI bin Muhammad RASID and I will present the question 1. Question 1 is about every cyclic group is abelian. Next, for definition, a cyclic group is a group that can be generated by a single element X, the group generator. Cyclic groups are abelian. An abelian group is a group for which the element commute, for example, A times B equal to B times A for all elements A and B. Abelian group therefore correspond to group with symmetric multiplication table. All cyclic groups are abelian, but an abelian group is not necessarily cyclic. All subgroups of an abelian group are normal. In an abelian group, each element is in a conjugacy class by itself, and the character table involves powers of a single element known as a group generator. Next, for proof of theorem, let G be a cyclic group and let A be a generator of G so that we have the set of A to the power of n such that n is in integer. If G1 and G2 are any two elements of G, there exists integer R and S such that G1 equal A to the power of R and G2 equal A to the power of S. Then we obtain G1 times G2 equal A to the power of R times A to the power of S. From the properties indices, A to the power of R plus S, which is same as A to the power of S plus R, because the base is same. Then we obtain A to the power of S times A to the power of R, which is same as the G2 times G1. Since G1 times G2 is equal to G2 times G1, therefore G is abelian. Example for theorem, suppose that we choose a group which is integer modulo 6 under addition. Integer modulo 6 is consists of element 0, 1, 2, 3, 4, and 5. Then we need to find the subgroup generated by each of the elements. First, the subgroup generated by element 0 is only 0. Next, the subgroup generated by element 1 is 0, 1, 2, 3, 4, and 5. Next, the subgroup generated by element 2, 0, 2, and 4. Next, the subgroup generated by element 3 is 0 and 3. Next, the subgroup generated by element 4 is 0, 4, and 2. And lastly, the subgroup generated by element 5 is 0, 5, 4, 3, 2, and 1. So, we can see that integer modulo 6 is generated by two elements which are 1 and 5. Hence, integer modulo 6 under addition is a cyclic group with 1 and 5 as its generator. Then, we want to prove that integer modulo 6 under addition is abelian. Let integer modulo 6 be a cyclic group and 1 be a generator of integer modulo 6, that we have the set of 1 to the power of n such that n is in integer. If 2 and 3 are two elements of integer of modulo 6, there exists integer R and S such that 2 equal to 1 to the power of R and 3 equal to 1 to the power of S. Then we obtain 2 times 3 is equal to 1 to the power of R times 1 to the power of S. From the properties indices, 1 to the power of R plus S, which is same as 1 to the power of S plus R, because the base is same. Then we obtain 1 to the power of S times 1 to the power of R, which is same as 3 times 2. Since 2 times 3 is equal to 3 times 2, hence group integer of modulo 6 under addition is abelian. Therefore, we can conclude that every cyclic group is abelian. That's all from me. Thank you.
Question 2 is about Kelly's theorem where every group is isomorphic to a group of permutation. Permutation group is a group of permutation on a set, and permutation on a set is bijection of a set to itself. The corollary of Kelly's theorem is every finite group G of order n is isomorphic to a subgroup of symmetric group of n. In order to prove, let G be a group. The function phi G maps to symmetric group of G is defined by phi of y equal to lambda y, where lambda y of G equal to yg. For all G in G is called the left representation of G. To show that lambda y is a permutation, it should be verified that lambda y are 1 to 1 and on 2. First, we need to verify that lambda y is 1 to 1. For any Rs in G, lambda y of R is equal to lambda y of S. Since the previous slide, we have said that lambda y of G is equal to yg, so here we will get yr equal to ys, and by the cancellation, we will get r equal to s. Next, we need to verify that lambda y is onto G. So, for any s in G, lambda y of y inverse times s is equal to y inverse times s. And by the inverse element property, we will get the answer is equal to s. So, with this, it verifies that lambda y is a permutation. Proof for the theorem. Let G be a group, then the left representation provides a map phi G maps to symmetric group of G defined by phi of y is equal to lambda y. Here, we need to verify that phi is a group of homomorphism and phi is 1 to 1. First, we need to verify that phi is 1 to 1. Suppose that Rs in G and phi of R is equal to phi of S. Then, phi of R is equal to phi of S. By the previous slide, we have said that phi of Y is equal to lambda Y. So here we will get lambda R is equal to lambda S. Then, we multiply both sides with identity. Since in the definition, we have said that lambda Y of G is equal to YG. So here we will get RE is equal to SE. Since any number multiplied by identity will get itself, so here we will get R is equal to S. Thus, it proves that phi is 1 to 1. Then, we need to verify that phi is a group of homomorphism. Let Rs in G, then phi of Rs is equal to lambda Rs. And phi R phi S is equal to lambda R lambda S. Here, we need to show that the two permutations lambda Rs and lambda R lambda S are the same. So, we let G in G, then lambda Rs of G is equal to Rs times G. By using the associative law, we will get R times Sg. And we know that R is equal to lambda R times Sg. Since R is equal to lambda R and S is equal to lambda S, by using associative law again, we will get lambda R lambda S times G. Since lambda Rs is equal to lambda R lambda S, which implies that phi of Rs equal to phi of R phi of S. Thus, here shown that phi is a group of homomorphism. So, we have shown that phi is 1 to 1 and it is a group of homomorphism which completes the proof. Example for the theorem. Show that the group of G have the element of 1 Rs is isomorphic to a group of permutation. Here, we will solve this problem by using the multiplication. First, fill the first row and the first column as the same in the heading. Then, the rest, we need to compute it. Okay, for the S times R, we need to put 1 and not S. Why? It is because in every row and column, each element will be appeared only once. So, automatically, when R times R, we will put S. Next, when S times S, we will put R, since in the row and the column already contains 1 and S. Then, automatically, we will put 1 when R times S. From the table, we will get equal the cycle notation 1 as all the elements in the group of G maps into itself. We will get cycle notation 1 Rs as 1 maps to R maps to S, and S maps to 1. We will get cycle notation 1 SR as 1 maps to S maps to R, and R maps to 1. Therefore, G is isomorphic to the subgroup of G prime where element of the subgroup G prime consists of the cycle notation of A, B, C.
That's all from us. Thank you.